To iterate something means to repeat a process. An iterated integral is an integral of integrals. The idea is initially intimidating, but once you understand the picture, you'll see it's not so bad. Imagine that we have some function f sitting above a rectangle. We saw in the previous section that the double integral of f over the rectangle is the volume beneath the function. Our goal is to figure out how to use our integration knowledge to calculate the volume. Following the traditions of calculus, we want to imagine how we might cut this task up into little pieces and then add them all together. We're going to start by making thin slices parallel to the YZ plane. Notice that this is like a trace because this is a region where x is basically constant, except it has just a little bit of thickness. We'll call that thickness dx. Then the volume of that slice is going to be the area under the curve multiplied by dx. And to find the area under the curve, we can use our single variable integration techniques. Notice that the lower endpoint is c and the upper endpoint is d, so that we can express the area as an integral. This is a dy integral, which implies that x is some fixed value. This formula gives us the area of the cross-section, and then we get the volume of the thin slice by multiplying it by dx. To get the total volume, we need to add up all these individual volumes. From here, we just make a substitution. We usually drop the parentheses and use position to tell us which limits correspond to the integration. You can always put the parentheses back in if you get confused, or you can also explicitly include the variable of integration in the limit. The language can be a bit confusing. A double integral is the conceptual object we created when we took a double Riemann sum and took the limit as the partition got smaller and smaller. An iterated integral is the specific process of calculating a double integral by first integrating with respect to one variable, then the other. It is an integral of integrals. This distinction is subtle and is not something that will likely cause problems, but it's worth keeping in mind. We can do this process again, but make the slices parallel to the xz plane. It turns out that the result is very similar. Intuitively, we would think that the answer we get should be the same since it's the same total volume. And while it's not true in general, it's true for continuous functions. And this result is known as Fubini's theorem. Theorem: if f is a continuous function on a rectangle R, then the double integral can be calculated as an iterated integral in either order, and the result of both calculations will be the same. When calculating these integrals, the biggest point of struggle for students is keeping track of the variables. When you're integrating with respect to x, all the y variables are treated as constants. And when you're integrating with respect to y, all the x variables are treated as constants. And when you plug in the limits, make sure you plug into the correct variable. It takes time and practice to really get comfortable with this, but it's not because it's hard. You just need the practice of mental organization and keeping the information straight.